So good afternoon, everyone, and welcome back. This session is focused on lightweight cryptography. And for this session, we have as a session chair, Professor Christoph Pitzak and Dr. Shweta Vandari. So over to you to the session chair.
Okay, thank you for the introduction. So welcome everyone to this second paper session of this year's Indocrypt. So I said it's on lightweight cryptography, and we have three exciting presentations today. Or in this session, the first one is on a 3-input exclusive OR gates support for Bioparatus algorithm. And the speaker is Vishnu Ashutosh Dasu. So Vishnu, please take the stage.
Thank you. Thank you for the introduction. So I'm Vishnu Dasu from TCS Research. I'll be presenting our paper titled 3-input exclusive OR gate support for Bioparatus algorithm at Indocrypt 2021. This is a joint work with Anubhav Bakshi, Vanshi Karmakar, Anupam Chattopadhyay, and Takanori Isobe. Here is the outline of the presentation. First, I'll be introducing the problem statement. Then I'll be discussing some of the background and prerequisite knowledge required to interpret the results in solution. Next, I'll be presenting two solutions to the problem. One is an adopted solution from existing work, and the other is a new solution which has been proposed by us. Finally, I'll be presenting some results and wrapping up with the conclusion in future works. The linear layer is an important component of the modern-day Cipher since it is responsible for spreading diffusion to the entire state. For example, in the AES block cipher, the mixed column operation is one of the primary sources of diffusion. These linear layers can be expressed as binary, non-singular matrices and can be implemented using XOR gates only. The Bioparatus or BP algorithm was proposed to find efficient implementations of these linear layers using XOR2 gates. While the original version has been presented over a decade ago, there have been multiple works in the recent past which aim at further improving the efficiency and cost of these implementations. However, most of these works consider XOR2 gates only. In the solution that we present, we generate efficient implementations of these linear layers using both XOR2 and XOR3 gates. Now I'm going to discuss some of the different notions of XOR count, which are used to define the cost of an implementation of a linear layer using XOR operations. The direct XOR or DXOR count of a binary matrix is defined as the Hamming weight of the matrix minus the number of rows. The sequential XOR or SXOR count of a binary non-singular matrix is defined as the minimum number of XOR operations of the form xi is equal to xi XOR xj. Here we can see that these are in-place XOR operations since the xi variable appears on both the left-hand side as well as on the right-hand side of the equation. The branch epsilon XOR count or B epsilon XOR count of a binary matrix is defined as the minimum of the summation of Ci Ei for I equal to 0 to epsilon. Here, Ci and Ei correspond to the cost of a number of XOR operations with I plus 1 inputs. For example, the XOR2 operation appears E1 times and is of the form Ti is equal to Tj0 XOR Tj1. So here we can see that unlike the SXOR count, these operations are not in place. C0 and E0 correspond to the cost of a number of copy operations respectively. In a hardware implementation, normally these copy operations can be considered to be free of cost since they can be achieved using a simple wire. However, in a software implementation, a copy operation as well requires some clock cycles. Here's a small example to visualize the different notions of XOR count on a 5x5 matrix. So the DXOR count of this matrix is 6, the B1 XOR count is 4, and the SXOR count is 5. So we can see that the B1 XOR and SXOR counts achieve a lower cost since they reuse the variable X0 XOR X1 to implement the Y2, Y3, and Y4 outputs of the matrix. So the B1 XOR and XOR counts are upper bounded by the DXOR count. In other words, the DXOR count can be considered to be the cost of the naive implementation of the matrix using XOR operations. A straight linear program or SLP is a sequence of XOR operations which defines the implementation of a linear circuit. The depth of a logical circuit is defined as the number of combinational logic gates in the longest path of the circuit. For an example, if you take an SLP and if you assume that the input variables are at depth 0, then the depth of the circuit can be computed as the maximum of the depths of the variables on the right-hand side plus 1. Here, I'll be discussing the working of the BP algorithm. The BP algorithm is an iterative algorithm whose global state is maintained by two vectors, known as the base vector and the distance vector or dist vector. For n by n matrix, the base vector contains n elements which correspond to the n inputs, and the dist vector contains n elements, where each element is the Hamming weight of the rows minus 1. For example, if we consider the previous 5 by 5 matrix, the base vector would contain 5 elements, which are x0 to x4, and the distance vector would similarly contain 5 elements, where each element is Hamming weight of the rows in the matrix minus 1. So we can observe here that initially, the sum of the elements of the distance vector corresponds to the dxor count of the matrix. Next, once the base vector and distance vector initialized, we generate all n choose 2 combinations of the base vector element and compute their sum. Here, the sum is simply an XOR 2 operation. Then we create a copy of the dist vector called DC vector and assign it to each of the combinations. Next, for each combination, we check if it's possible to implement the ith row of the matrix using disc of I minus 1 base elements if that particular combination added to the base vector. If it is, then we reduce the element in the disc vector by 1. So essentially what this step does is it determines whether the number of XOR operations required to implement the rows in that matrix can be reduced by 1 if a particular combination is generated. Once this step is repeated for all combinations and for all rows in the matrix, we then determine the most suitable combination that needs to be inserted into the base vector. This is normally done using a heuristic. So one example of a heuristic would be to pick that combination with the least L1 norm and L2 norm of its corresponding disc vector. Once we identify the most optimal combination, we insert that to the base vector and update the dist vector with the corresponding disc vector of the combination. Next, we look for all elements in the dist vector which are equal to 1. So this means that that particular row can then be implemented using one XOR 2 operation involving a pair of elements from the base vector. So we identify such elements, set them to 0, and finalize the implementation of that row. Then we check whether all the elements of the dist vector are 0 and repeat this process until they are. So we can see here that this iterative process is repeated basically until all the rows of the matrix are implemented. Here's an example of the output of the BP algorithm in SLP format for the 5 by 5 matrix. So we can see here that the implementation of the matrix takes 4 XOR 2 gates, and this corresponds to the B1 XOR count. And we can see that the BP algorithm was opted to choose the X0 XOR X1 combination to insert in the base vector. This is because this particular operation appears in all of the outputs, namely Y2, Y3, and Y4. And this basically in the heuristic, if we take the L1 norm, L2 norm of the corresponding disc vector for this combination, then that is the least. So these are some of the logic libraries that we have considered to evaluate and benchmark the performance of our algorithm. The gate count or GC simply corresponds to the number of XOR 2 and XOR 3 gates in implementation. And ASIC 1 to ASIC 4 are 4 different processes. And the cost of the XOR 2 and XOR 3 gates in those processes is defined in terms of gate equivalent or GE. In this section, I'll be discussing an adopted solution to add XOR 3 support to the Bioparatus algorithm. This was proposed by Bunny et al. At IWC 2019. So this is a post-processing algorithm where we take an SLP returned by the Bioparatus algorithm with XOR 2 gates only, and then add XOR 3 support later on. The first step is to look for all instances of T variables in the SLP which have fan out of 1. So here a T variable is an intermediate variable in the SLP which is not the final output of the matrix. And a fan out of 1 means that this particular variable is used only in one other variable. So for example, if you consider the following snippet of the SLP, T4 is equal to X0 plus X6 and T20 is equal to X1 plus T4. So if this T4 variable is used only in the T20 variable, that means this T4 variable now has a fan out of 1. We can then eliminate the T4 variable and update the T20 variable with an XOR 3 operation. So by repeating this process for all the T variables in the SLP which have fan out of 1, we can introduce XOR 3 support to the Bioparatus algorithm after it has been generated using XOR 2 gates only. So we know that this approach does not take into account the relative cost of XOR 3 in the logic library. In other words, the output of this algorithm is going to remain the same given that the input SLP does not change. Now I'll be discussing our new solution to extend the functionality of the BP algorithm to support XOR3 gates. So the first step is similar to before, where we initialize the base vector and dist vector. Next, we generate all n-choose2 pairs and n-choose3 triplets of the base vector elements and compute the sum. So here the sum corresponds to the XOR2 and XOR3 operations for the pairs and triplets respectively. Next, we assign a copy of the dist vector called distc vector to each of the pairs and triplets. Then for each XOR2 combination, we determine whether it's possible to reduce the elements of the distc vector by 1. And similarly, for each of the XOR3 combinations, we first check if it's possible to reduce the elements of the distc vector by 2. And if it's not, we check if it's possible to reduce them by 1. So this operation is then repeated iteratively for all combinations and for all rows in the matrix. Next, we determine the most suitable combination to be included into the base vector based on a heuristic. So unlike the original version, the heuristic now also takes into account the relative cost of XOR3 in the logic library. So once this is complete, we then add the combination to the base vector and then look for all elements in the dist vector which are either equal to 1 or 2. So the elements equal to 1, that means that particular row in the matrix can then be implemented using one XOR2 operation involving a pair of elements of the base vector. And if it's equal to 2, then the row can be implemented using one XOR3 operation involving 3 elements from the base vector. Similar to before, this is repeated iteratively until all elements of the distance vector are 0. So this approach is different from the post-processing approach proposed in IWSec, because now we account for the relative cost of XOR3 by incorporating it into the heuristic. Here is a summary of the implementations of the Aes Mix Call matrix using the algorithms proposed in recent works. So to reiterate, the B1 XOR and S XOR notions only account for XOR2, and the B2 XOR representation accounts for both XOR2 and XOR3 gates. So we can see here that the algorithm proposed by the results from our algorithm achieve the lowest gate count and depth in the circuit of 59 and 4 respectively. Here are some results on a few 16 by 16 matrices. The cells highlighted in gray correspond to those scenarios in which our algorithm has performed better than the IWSec algorithm. So for example, we can see here that for the jolting matrix, in all of the logic libraries, the result of algorithm has the output of algorithm is a lower cost as compared to the IWSec algorithm. And similarly, in the gate count metric for all the matrices, our algorithm has managed to generate a lower cost implementation. These are a few results on some 32 by 32 matrices. Similar to before, the cells in gray correspond to those scenarios in which our algorithm has performed better than the IWSec approach. So for the two-fish matrix, we can see that for all of the logic libraries, the output of our algorithm is better. And similarly, for the gate count metric, the output of our algorithm is better for all of the matrices. Here's an interesting visualization of the Aes Mix Call implementation in a graphical format. So this is the implementation with 59 gate count and depth 4. So the nodes in yellow correspond to the inputs which are at level 0 or depth 0. And the subsequent layers of the graph correspond to the different temporary variables and outputs of the matrices, which are the XOR operations, either XOR2 or XOR3, which involve the elements from the previous layers. So you can see here that there are 4 such layers, and this corresponds to a total depth of 4 in the circuit. So to conclude, our work achieves the best known results in terms of a logic library using XOR2 and XOR3 gates. And several of these results are reported for the first time literature. For example, the implementation of the Aes Mix Call matrix with 59 gate count, depth 4, and 258.98 gate equivalent in the ASIC4 library. Our work also paves the way for multiple future works that we have undertaken. So one may also consider the inclusion of XNOR gates as well as higher input XOR gates, such as XOR4 and beyond in the implementation. Similarly, the reversible implementation, depth optimization, as well as cost for the inverse matrices is an interesting direction of study. So a majority of the current works only focus on reducing the cost of the circuit without focusing or looking into optimizing for the depth as well. So all of the source code can be found at Bitbucket at the following URL. The implementation contains our algorithm as well as the IWSec algorithm to generate and extend the functionality of the Bioparatus algorithm to incorporate Exotherm gates. Thank you.
Thank you, Vishnu, for this excellent talk. Let me see if there are, I don't see any questions in the chat. So maybe let me ask some questions first.
Yeah, any live questions?
Live questions, of course, yeah.
Anyone? So I would like to ask one question, Vishnu. You have mentioned that the accepted solution remove T variables on the cost of increasing number of XOR operations, right?
They introduce XOR3 operations by limiting the T variables. Yes.
So how your approach actually balance this trade-off? So when you remove a variable, you are increasing the number of XOR operations. So how your approach balance this one?
So our approach is not a post-processing algorithm. So we incorporate the support for XOR3 during the Bioparatus algorithm itself. So if you look at the original implementation of the Bioparatus algorithm, each nChoose2 combination corresponds to an XOR2 operation. And we extend this functionality by taking nChoose3 combinations of your base vector elements. So now each of these nChoose3 combinations, correspond to an XOR3 gate introduced in the logic circuit.
Okay, all right, thank you.
Okay, thanks. Any more questions live or in the chat? Otherwise, maybe I can have a short question. So the problem you solve, very much looks like optimization problem. So I guess you could cast it somehow as optimization problem, and assuming you can do that, can you somehow quantify how close to a theoretical optimal solution you are? And maybe in complexity terms, say how hard would it be to actually find, solve this problem optimally and find an optimal solution, or is it not even well defined?
Yes, correct. It is an optimization problem, and so I don't think there are any theoretical results that see how close to optimal that we are come yet. But there have been more and more interesting solutions that have been proposed to improve the efficiency more. So recently itself, there have been one solution to generate the implementation of the Aes Mix Call matrix using 91 XOR2 gates, and the previous higher was 94. So currently looks like it's still possible to push the boundaries further to achieve more better cost implementations.
Okay, thanks. Any more questions? I think otherwise, thanks for the presentation, and we can move to the second talk of this session, or should we wait till it's exactly 12? I guess we can just move on, right? And then have more time for the questions at the end of the session. So the second talk in this session is going to be pushing the limit, searching for implementations with the smallest area for lightweight S-box. The paper is by Zhengyu Lu, Wei Wang, Kai Hu, Sang-Xiu Pang, Liu Xiaowu, and Meiping Bang. And Zhengyu Lu will present the talk.
Yeah, thank you. Thank you for the introduction. Maybe you can see it.
Yes.
Yeah, can you see? Okay, thank you. Well, hello everyone. My name is Zhengyu Lu. I come from Shandong University, China. Today, my topic is pushing the limits. Pushing the limits, searching for implementation with the smallest area for lightweight S-boxes. This is joint work with Weijia Wang, Kai Hu, Yan Hongfan, Li Xuanwu, and Meiqing Wang. Lightweight cryptographic primitives are deployed more and more in such-constrained devices. Specifically, the S-box should be well considered since they are the popular and costly components in manipular ciphers. The designer of lightweight cryptography needs to consider both the security properties and the implementation performance. The hardware implementation performance includes area, throughput, latency, and so on. The area cost is an important criterion, and we focus on it in this work. However, to our best knowledge, there is no efficient method to search for an Xbox's implementation with the smallest area. Here, we briefly introduce two mainstream methods to find the implementation of an Xbox, which are the heuristic algorithm and set-based search algorithm. Firstly, in the domain of logical synthesis, several heuristic algorithms provide satisfactory solutions, such as Boom and Espresso, which are probably implemented in many commercial synthesizers. Automated Tor lighter proposed by Jen et al. uses graph-based meet-in-the-middle search algorithm. It is under the assumption that every instruction is invertible. Despite of the efficiency, this algorithm relies on some heuristic and are infeasible to prove that their results are optimal. Then at FSE 2016, Dolphin proposed a set-based method. This model can find the implementation of an Xbox with the smallest number of gates. However, the area costs of different gates are different. The smallest number of gates will still lead to a large area cost. So our goal is to search for the smallest area cost implementation of Xboxes on the set of combinatorial gates. To measure the area cost under the different library, we use gate equivalent as a euro unit. One gate equivalent is equal to the area of two input NOR AND gates, and the area of other gates can be normalized by using the ratio between their area and the NOR AND gates. In the library of UMC 180 nanometers, the area cost of typical gates are listed in table 1. In our work, we consider these 2, 3, and 4 inputs gates. The complex gates will with multiple inputs can save the area significantly. Since our tool can be regarded as an improved version of Stofflin's model, we first briefly introduce his method. He proposed a binary model to solve the decision problem. Is there a circuit that uses at most key logic operations to implement an Xbox? For example, there is a 2 bits Xbox and its lookup table. Is there a circuit that uses 3 gates to implement the Xbox? If it exists, what about the 2 gates? We encode the decision problem into 2 steps. For the first step, we use binary variables to constrain the Xbox, just like the row with the red line. We let x0 equal to 0, x1 equal to 0, and so on to denote that s0 equal to 3. The s1, s2, and s3 are expressed in the same way. For the second step, the variable t represents the gate, and the variable q is the input of a gate. Each q must be one of the Xbox input or the output of one previous gate. This can be constrained by the variable a. For example, the inputs of gate T0 are Q0 and Q1, and each of them can be one of X0 or S1. Next, the inputs of gate T1 are Q2 and Q3, but Q2 can be one of X0, X1, or T0. The output variables Y are similar to Q. They should be one value from previous gates. Note that this set of equations can only encode that S0 is equal to 3. We need another 3 sets of equations like this to encode the 2 bits Xbox. In general, Stoffen's model includes every gate as an algebraic normal form equation. The variable b determines the type of a gate. For example, when the triples b equals to 0, 1, 0, T is an XOR gate and represents Q0 XOR Q1. This model is such for an implementation with smallest number of gates. It does not need to encode the NOT gate because the NOT gate can be replaced by other larger gates. We can see from these two equations, the number of gates will not increase and in both cases. However, when we consider the area cost, the NOT gate cannot be ignored. Next, I will give an overview of our work. Firstly, we re-encode the NOT gate and 2, 3, 4 input gates into the model. We produce an implementation with a set of K gates, and we denote this set as I. Then we add the area cost of each gate up to obtain the area of this implementation. The equation below is naturally the objective function of our new model. The new model can determine whether a circuit can implement an S-box with K gates and G area cost. As mentioned before, implementation with the smallest number of gates is not the one with the smallest area. Therefore, we need to determine the range of area costs and the number of gates. For details, we use B2 times Q0. We use B2 times Q0 to encode the NOT gate. In fact, any logic operation can express as an algebraic normal form equation. The right function shows how to encode this 3 inputs and 4 inputs complex gates, such as 3 input and 3 input XOR. In general, this is the framework of our model to encode an 4 bits S-box. S0, S1, S2, S3 are the inputs and Y as the outputs of an S-box. Q4, Q5, Q6, and Q7 are the inputs of T1, and Q4 can be one of the S0, X1, S2, X3, or T0. This encoding method has to determine the number of gates in advance. Then we can use Stoffen's model to get an implementation with the smallest number of gates, kilo. The area cost of this implementation is denoted as GAP. So the K must greater than or equal to kilo and no more than GAP. Otherwise, even if all gates are NOR AND gates, the area cost will be greater than GAP. Then we only need to search for the implementation with the smallest area cost in the range by using the set solver. Let's review the encoding method. For an n-bit S-box, we need 2 to the power of n sets of equations to encode each input x and output sx. In the previous example, each input and output of the S-box needs a set of equations to constrain. When using the set solver, the efficiency would be lower as the number of variables increases. So we use bit slice technique to reduce the number of variables. For example, when considering the S-box of a rectangle, we encode every variable as a 16-bit Boolean vectorial variables, and uppercase X0 represents the most significant bit of each input. So X1, X2, and S3. In this way, we need only one set of equations to re-encode our model at the cost of 16 bits per variables. But this will reduce a lot of intermediate variables. Finally, we apply our method to many S-bosses and compare our results with lighter and softless tool. We managed to find an improved circuit of rectangle S-boss with 18 gate equivalent cost, which is better than lightest result. And we can verify that the circuits of Piccola, Skinny, and L-blocks S-bosses have the optimal area costs under the 2, 3, and 4 input gates, which we considered. In addition, due to the bit slice technique, our model is also useful in finding the implementation of the 5 bits S-bosses, such as Ketchak and Escon. In addition, we also use the state-of-art synthesis tool, Synopsys design compiler, to synthesize the lookup table-based implementation and the equation-based implementation from 3 walls. The synthetical results are the same as we expected. So this also verifies our results. Okay, that's all. Okay, that's all. Thanks for your attention.
Okay, thank you, thank you. Any questions? I don't see any in the chat, but maybe I have a question. Or no, maybe let's the audience ask first, of course, if there's any questions in the audience.
Yeah, there is one question.
Yeah.
Hello. First of all, a very nice presentation and very interesting research problem. So in one of the slides, you have mentioned that less number of gates does not mean that area is less. So if we believe in theory, that should be true. So if you have any contradictory example or anything to prove your point, or like for us to believe that it is to be true.
Any examples? Sorry, I don't remember it clearly. We apply our model in many S-bosses. Maybe I think I will.
No problem. Just like I thought, in theory we believe it to be true, but since you are saying so, it would be interesting to hear it out. Like, how did you come to that conclusion?
Sorry, how I?
Like, you have written the statement there that less number of gates does not mean less area or less output area. In one of the slides, I think slide number 4 or 5, you have mentioned the same.
Okay. Okay. Maybe for example, in the work of in the FSE 2016 softness work, he give many results about. I remember that one result about the Piccolas S-boss give us 10 or 8 gates, and its area cost is not the lowest one. And in our work, we find that the results given by lighters is optimal.
Okay, thank you.
Yeah. Thank you.
Any other questions?
Any other question? No from live session.
Actually, I had a similar question. I was surprised that you only optimized the number of gates. And, I remember from my times as a student when we had to program FPGAs, it was really terrible with all those wires, right? You had like a nice circuit, but then actually implementing it, you had all these crossings and wires were long, but you're not optimizing at all for wires, if I understand, or numbers of crossings or things like that. You kind of optimize for number of gates, and then you run you compute the area on top of that. So would it make sense to take into account topological aspects or numbers of crossing or all these things?
Sorry, I can't answer your question.
I'm totally out of the field, so maybe my question doesn't make much sense. But I was just surprised that you optimized just the number of gates, as opposed to I think what is much more complicated, namely the area, which. But maybe maybe the number of gates is already a very good approximation for the area, so you don't have to bother about the wiring in the first approximation step.
Maybe the question is the number of the gates and the area of cost. How to what's the difference between area cost and the number of gates?
Yes, but you can also take this offline. No, my question exactly. My question would be simply that you almost equate the area size with the number of gates. I mean, I see that the number of gates is important, but the number of if the gates are all far apart and you don't need long wires that kind of go all over the place, that should hurt, But maybe Xboxes are small enough for that not to matter. I don't know.
Yeah. Number of gates is important too, but in some constraints, in the source constraint devices, we think the area and maybe the latency are the most important than the number of gates. But in some advanced cryptographic, like the MPC and the key knowledge, the number of gates is important.
Yeah.
Sorry.
Okay. Yeah. No, for MPC. No. Okay. Nancy, for MPC, it's only the number of gates, of course.
Yeah.
Okay. Thank you.
Yeah. Thank you.
If we have no more. Yeah. Okay. I think we have no more questions. Then maybe we can move to the last talk of this session, which is entitled Quantum Resource Estimation for FSR-based Symmetric Ciphers and Related Groovers Attacks. And Arpita Maitra is giving the talk.
Yeah.
Arpita, please.
Yeah. I'm here. So thank you. So now I am sharing my screen. So is it visible, right? It is visible now? Okay. So today we are going to talk about the paper entitled Quantum Resource Estimation for FSR-based Symmetric Ciphers and Related Groovers Attacks. Authors are Ravi Anand, Urpita Mitra, myself, Shubhomay Mitra, Chandrasekhar Mukherjee, and Saurabh Mukhopadhyay. Authors are from Indian Statistical Institute, TCG Crest, Kolkata. I am from TCG Crest, Kolkata, and Indian Institute of Technology, Kharagpur. The outline of the talk is as follows. So first we will discuss some preliminaries like qubits, quantum representation of a Boolean function f, Grover search algorithm. Then we will discuss how to estimate the resources for FSR-based ciphers like Grain 128, AEAD, Tiny Jumbo, Lizard, and Grain P1. Then we will discuss the security under NIST's max depth and conclude the talk. We all are familiar with classical bit 0 and 1. Those are the basic elements of our classical computers. The quantum counterpart of classical bit 0 is Kate 0 and classical bit 1 is Kate 1. These Kate 0 and 1 are the main mathematical objects in the quantum paradigm. Physical counterpart is a photon. Qubit has a unique property, that is, it can be expressed as the superposition of 0 and 1. Thus, a qubit can be written as follows: alpha 0 plus beta 1, where alpha beta are complex number, and mod alpha square plus mod beta square equal to 1. Now, Boolean function, we all know that Boolean function is a function which maps 0 to the power n to 0, 1. So it is an input, one output function and not reversible. But in quantum domain, quantum gates must be reversible. So we have to add n inputs to n outputs and add another input y and output y or fx. Now we have n plus 1 many inputs and n plus 1 many outputs. Now the function is reversible. This function, this reversible function, we will call it UF. So reversible version of this F. If implementation of F in classical domain requires T and many gates, then the implementation of UF, which is the classical version of this F, in quantum domain will require order of t n many gates. UF should be designed in quantum framework that is using quantum gates. Now, Grover algorithm. In Grover algorithm, we also we will use we have to use some Boolean function f, which maps 01 to the power n to 01, and the function is like this: fx will be 1 for some x, and for all other x it will be 0. Classical algorithm will require 2 to the power n many queries to find this x, this marked element. But if we use Grover's algorithm, then we can find this x in worst case using 2 to the power n by 2 many queries. So it is giving, Grover algorithm is giving some speed up over classical domain. The most important element in this algorithm is a small block of code called Grover's iteration, that is G. G consists of n many Hadamard gates, UO bar, n many Hadamard gates, and UF. UF is the oracle that marks the element of interest, and UO bar is the operator that flips the face of all the basis states except all 0 states. In UF, we have to use some Boolean function f, and the Boolean function is as follows: fx will be 1 if x equals to x0. x0 is our target element, our marked element. So fx will be 1 for x0 and 0 otherwise. If we use this UF on some states x and y, we will get x and y's or fx. Similarly, if we apply UO dagger, this is also a unitary gate. If we use this UO bar on some state x, we will get minus x if x not equal to all 0, and we will get x if x equal to all 0. The matrix representation of this UO bar is this. Now we will see, and this is the circuit for Grover algorithm. So in Grover algorithm, this is G. In Grover algorithm, we have to start with n number of zeros and n number of Hadamard gates to create equal superposition of all 2 to the power n many bit patterns. And here y should be 1 by root 2, 0 minus 1, and that is why we have to start with 1 and 1 Hadamard gate. So here n many registered and here 1 registered. This so total n plus 1 many registers. This n plus 1 many register will go through this UF. UF outputs here n many registers and here y's or fx. This first n many register will go through n number of Hadamard gates, then UO bar and n number of Hadamard gates, and this portion will be repeated root n many times. And due to this iteration, the amplitude of the targeted element will be amplified, and that is why when finally we will measure this first n many register, we will, with a very high probability, we will get the targeted element. Now we will see how we can use this idea in finding the key in stream cipher and block cipher. So first we will discuss stream cipher and then we will go to block cipher. For stream cipher, for any key k, 01 to the power k, and initialization vector iv, 01 to the power m, let the key stream be skiv, which we will call ks. Since the initialization vectors are generally assumed to be known, we can write sk equal to ks. Thus, the Boolean function f for the Grover oracle uf would be like this: fk will be 1 if sk equal to ks and 0 otherwise. For block cipher, let E be a block cipher with block size n and key size k. For any key k, 01 to the power k, let EKM be the encryption of plain text m under the key k. For a given plain text cipher text pair m and c, where c equal to EKM, fk will be 1 if ek0m will be c. Here k0 is that secret key and 0 otherwise. It is possible that there exist other keys which generate the same key stream for stream ciphers or same cipher text for known plain text in case of block cipher. So, to increase the success probability of the attack, we need to extend the search for more key stream in case of stream cipher and for more plain text cipher text pairs in case of block cipher. Interestingly, the corresponding increase in the circuit size is different for block cipher and stream cipher. We will see that. For block cipher, assume a block cipher having a block size of k bits. let the key k be of size k. Ck, the encryption function, it maps 01 to the power k to 01 to the power k. For t blocks of this cipher text, the collision probability will be like this: 2 to the power k minus 1, I varies from 1 to t, product of 1 by 2 to the power k minus I minus 1. Now, put t equal to 2. That means we are now considering only two blocks for that cipher. So if we set t equal to 2, then the probability of collision will be order of 2 to the power minus k. We need, so here we set two blocks. So that is why we need 2k bits of cipher text in each application of the Grover oracle to evaluate the cipher which adds to the circuit size. Contrary to this, in case of stream cipher, we will see that the adversary gets advantage to mount Grover. So in case of stream cipher, what will happen? Consider the key stream k subsize rho and the key k of size k, where rho equal to k plus c, where c is some constant. It can be shown that in this case, the collision probability will be order of 2 to the power minus c. So even for c equal to 10, we have a very low probability of collision. Thus, here we need k plus c many bits of cipher to mount the Grover, whereas in case of block cipher, we need 2k. So here order of k, but in case of block cipher, we need 2k. So this is the difference. So in case of stream cipher, we are getting advantage to mount Grover. This is the circuit for stream cipher. This is a circuit for Grover oracle in case of stream cipher. So you can find two blocks here, ENC and ENC dagger. ENC is the quantum implementation of the encryption function for the cipher, for the stream cipher. And ENC bar is the quantum implementation of the decryption function for that cipher. And in quantum domain, the interesting thing is that ENC, so this decryption function, that will be the adjoint of ENC, so encryption function. So quantum encryption function and quantum decryption function will be adjoint to each other. So that is why we use this dagger sign. Here we will start with equal superposition of all possible key. Then we will use encryption function. And this is our targeted key stream. This equal operator compares the output of ENC, encryption function of the cipher, with the given key streams, ks dash, and flips the target qubit if they are equal. ENC dagger is the decryption function. And after that, we have to apply in k many Hadamard gates, UO bar and k many Hadamard gates, and we have to repeat all this operation root k many times. Why k? Because our key size is k bit, so that is why we have to repeat this operation root k many times, and with a very high probability, when we will measure first k registers, we will find the secret key. In case of block cipher, we have to apply Grover parallelly. Here we are using two blocks. We are considering two blocks. That is why we are applying two Grovers parallelly. So first Grover, ENC dagger. Second Grover, ENC dagger. First Grover, our plain text cipher text pair is M1 C1, and for second Grover, our plain text cipher text pair is M2 C2. This equal operator compares whether the outputs from ENC is C1 and whether the outputs from ENC is C2. If outputs matches, then the targeted bit is flipped. And then we have to apply ENC dagger, and k many Hadamard gates, UO bar and k many Hadamard gates, and all the operation we have to repeat for root k many times. And then finally, we will measure first k registers and to find the secret key. So this is the circuit and here we consider a tiny jumbo is the block cipher. So that is why we wrote that Grover oracle using two blocks for tiny jumbo. So this is the circuit for stream cipher and this is the circuit for block cipher. Now how to estimate the resources. So in terms of Clifford gates, if we now want to count the number of Clifford gates in the circuit, then for stream cipher that will be this 2 into Clifford gates present in ENC. Why? Because if you if we see this circuit, the circuit for stream cipher, here we use only two blocks of ENC and ENC dagger, and that is why these two comes. And for block cipher, block cipher, we are using 4 blocks. For one, so this CNC dagger for first prover and the CNC dagger for second prover. So 4 blocks are used here. That is why this 4 comes. And why this 2K? Because we are considering 2 blocks for the cipher. That is why this 2K comes. So this is the this is for stream cipher, number of clipboard gates, and this is for block cipher. Here tiny jumbo for the number of clipboard gates. And if we consider T gates, so in terms of T gates, the number of T gates for stream cipher will be 32 into K plus 10 minus 84 plus 2 into T gates in ENC. This term comes from the C0 gate used in ENC. For block cipher, it will be 32 into 2K minus 84 plus 4 into T gates in ENC. This term comes from the C0 gate used in this ENC. And the total depth for both the cases, total depth will be 2 into depth of ENC. Now, this is the table where we provided the number of clipboard gates, number of T gates, T depth, full depth, and number of qubits used for these ciphers. So here we have to mention that what is meant by depth. A depth of circuit is the number of gates in row. Depth can vary depending whether we consider basic gates or composite gates. For example, if we consider Toffoli gate. So in terms of composite gate, the Toffoli gate, the depth of that circuit will be 1. But if we consider the basic gate, then the depth will be 12. T depth is the number of T gates in row, or in general number of any non-clipboard gates in row. This is the table for cost estimation. This is a table for cost estimation in case of exhaustive search. So in exhaustive search, what we did here, we multiply the first table, this table 1, with this factor pi by 4 2 to the power k by 2. So why we did this? Because we have to repeat the Grover 2 to the power k by 2. Actually, pi by 4 into 2 to the power k by 2 many times. This number of iteration is required. That is why when we have to estimate the cost for exhaustive T-search, we have to multiply each element of this table with this factor pi by 4 2 to the power k by 2. So this is the table. And now the max depth in this work, we have assumed that an adversary is bounded by a constraint on the depth of the circuit that he or she can use for Grover. NIST suggests a parameter max depth as such a bound, and possible values range from 2 to the power 40 to 2 to the power 96. We provide the gate counts for Grover search on both the stream and block ciphers under the constraint of max depth by a table, and this is the table. So NIST considered AES 128, AES 192, AES 256, and they provided gate counts for 2 to the power 40, max depth 2 to the power 40, 2 to the power 64, and 2 to the power 96. And from this table, you can see that in our case, the gates required for max depth 2 to the power 40, 2 to the power 64, and 2 to the power 96 are less compared to the max depth number of gates given by NIST. And thus we can conclude that all these ciphers, that is that grain 128, AEAD, lizard, grain V1, and tiny jumbo, fail to satisfy the security constraints. And in the summary, so in this work, we study quantum cryptanalysis of FSR-based symmetric ciphers like grain 128, AEAD, lizard, grain V1, and tiny jumbo. We study the cost of implementing Grover's research algorithm on these ciphers under the NIST max depth constraint. We found that all these ciphers fail to satisfy the security constraints. We observed that the increase in circuit size to reduce chances of getting a false positive is less first in ciphers is that we have implemented these ciphers in Qiskit and QHash environment, and all those codes are given in our paper. So thank you.
Thank you, Arpita, for this excellent talk. Are there questions on the stage?
Yes, any questions? questions? Okay. Hi, Arpita. It was a nice presentation and background was well explained, right?
Thank you.
I have one question. So as per your, observation, you said that stream cipher are much more prone to Grover's attack rather than block cipher, right?
No.
Okay.
I didn't say that.
Mhm.
Actually, for stream cipher,
Right.
stream cipher, if we want to the circuit, I said that the circuit size of stream cipher, when we mount the Grover on stream cipher, that will be lesser than the circuit size of block cipher if we want to mount the Grover on block cipher.
So for an adversary, like it is easier to have the attack on stream cipher or on block cipher?
And the circuit size is lesser for stream cipher and it is higher for the block cipher. But so if you say in that term, in term of circuit size, adversary get advantage to mount Grover on stream cipher rather than block cipher. Okay. But whether the security is less, so in terms of security, we can find that.
So what are your recommendations to protect the stream cipher specifically from such type of attacks?
No, this is not related to security actually. It is related to circuit size. Right. So if you want to mount Grover in stream cipher, then your circuit size will be less. And if you want to mount Grover on block cipher, then it depends on the how many blocks you want to you are considering. So here we are considering 2 blocks. That is why the difference is 2. It is not related to security. So it is.
So is it like if the circuit size is lesser, then the algorithm is faster, right?
Yes, but there is no that kind of straightforward relationship between the security, because here we are finding our motivation is to find the secret key. So in any way we have to repeat the Grover root k many times. So root k. So that's it. The issue how how long we have to iterate the Grover oracle. So for block cipher and stream cipher, for both the cases, we have to iterate that Grover oracle root k many times because the size of the secret key is k.
Right. Okay. Yeah. Thank you.
Okay, I see there's one question in the chat. Let me read it. Is the cost related to the implementation of encryption in... Oh, that's not the question. Is the cost related to
the implementation of ENC in quantum computer? Yes, in terms of gates and qubits, yes, it is related to quantum computers. Yes.
Oh. But so you always talk about circuit size, but I mean, what you probably mean is the number of quantum gates, Toffoli gates, or whatever that you have to evaluate at the end of the day. And my understanding was you said this is a factor 2, right? So basically 1 bit of security in some sense, if you want to.
So you are saying about that difference between stream cipher and block cipher?
Yes.
So
you always talk about circuit size. So what I understand, I mean, at the end of the day, it's just a number of, you can implement it any way you want. But the number of Toffoli gates you have to implement, if I understood correctly, for the same key size is a number 2 higher for block ciphers.
Block ciphers,
okay.
Yes.
Okay. So, in security terms, it would mean that there's like a 1-bit security difference between stream and block ciphers in the quantum setting. Okay, I don't even know what happens in the classical setting. Probably right. So, and so what is so you just talked about Grover's algorithm. I understand that this is the only generic one for finding, for dictionary search. But do you think that on, realistic ciphers, Grover is going to be always the best, or you think there could be something
Yes, there is Simon is also there, and there are many papers on the combination of Grover and Simon. Simon means Simon's algorithm in quantum domain. This is not the lightweight cipher Simon.
Yeah.
So yes, there are many papers. So where we can combine Grover and Simon and can achieve better result.
Okay. Are there any more questions from the audience or online? Otherwise, here. There's one more question. Does the size of circuit vary if we use different quantum simulation like QIS-Kit or Q-sharp?
Actually, in case of, we found that we only tried Qiskit and Q-hash. So for both the cases, the circuit size is almost same. So for both these cases, I don't know other simulators, but for Qiskit and Q-hash, for both the cases, the circuit size almost same, number of gates and almost same. We found that.
Okay, thank you. So if there are no more questions, then I would like to thank all the speakers again. I think you can clap on this. Let me see here. You can clap on this auditorium tool. And yeah, and I understand there is a tea break now.
Thank you.
Thank you.
So thank you for such a nice presentation, and thanks to the session chair, Professor Christoph and Dr. Mandari, for this session, for your time. Now I would like to request Dr. Jayaprakash Kaur to give the presentation, to give the mementos to the session chair present there. For the audience, you can also join the QA session directly to the authors through the Google Meet link that is shared in the platform itself during this tea break. And the next session will start within 15 minutes at 5:30 p.m. sharp.